Welcome to the session on geometric distribution. Consider a random experiment having only two possible outcomes, namely success and failure. We assume that the probability of success is the same for each trial and all the trials are independent. Now we define a variable x as the serial number of trials of the experiment in which the first success occur. Then we have to find the probability of x equal to x. That means the probability of getting first success in the xth trial. If we are getting the first success in the xth trial means the previous trials are, that means the previous x minus 1 trials are failures. That is, there exists, here we denote small p as the probability of success and q is equal to 1 minus p is the probability of failure. Then if we get the first success in the xth trial means there are x minus 1 failures, that is x minus 1 times q, and the xth trial is success. Then the probability of getting the success in the xth trial is equal to q into q into q into etc. into q, x minus 1 times q into p. That means q raised to x minus 1 into p. This is the probability mass function of the geometric distribution. That is, the definition of geometric distribution is a discrete random variable capital X is said to follow a geometric distribution if its probability mass function is given by f of x is equal to q raised to x minus 1 into p or p into q raised to x minus 1, where x varies from 1, 2, 3 etc. up to infinity and equal to 0 otherwise. Here p lying between 0 and 1 and p plus q is equal to 1. This is the definition of a geometric distribution. Here p is referred to as the parameter of the distribution. P is the parameter which lies in the interval 0 and 1. Now we can verify this f of x is a probability mass function. We know that for a probability mass function, a function is to be a probability mass function if and only if two conditions hold. First one is f of x is greater than or equal to 0 for all values of x, and summation over all values of x, f of x is equal to 1. Now we can verify these two conditions. Here p lying between 0 and 1 and p plus q is equal to 1 means q also lying between 0 and 1. If we put x equal to 1, we get f of 1 is equal to p into q raised to 0, that is equal to p, which is greater than 0. F of 2 equal to, that is if we put x equal to 2, we get f of 2 is equal to p into q raised to 2 minus 1 is 1, that is pq, which is also greater than 0 because p and q are in between 0 and 1. F of 3, if we put x equal to 3, we get f of 3 as p into q raised to 3 minus 1, that is equal to p into q square, which is also greater than 0, and so on. Therefore, we get all the values are greater than or equal to 0 for x equal to 1, 2, 3, etc. Therefore, the first condition satisfied. Now, we have to add all these probabilities. We get summation f of x is equal to where x is from 1 to infinity, that is equal to f of 1 plus f of 2 plus f of 3 plus etc. That is equal to f of 1 is p plus f of 2 is p into q plus f of 3 is p into q square plus etc. This is equal to, p is common, we can take p outside. Therefore, this is equal to p into 1 plus q square plus etc. That is equal to p into, this is the binomial expansion of 1 minus q raised to minus 1, that is equal to p into, here p plus q equal to 1 means 1 minus q is equal to p. Therefore, p into p raised to minus 1, that is equal to p raised to 0 is 1. That is the total probabilities is equal to 1. The second condition for a PMF is also satisfied by this function. Therefore, this is a PMF. Now, we have to find the arithmetic mean of the geometric distribution. Consider a random variable having the geometric distribution with parameter p, then f of x is equal to p into q raised to x minus 1, where x varies from 1 to infinity and 0 otherwise. Now, the arithmetic mean, simply mean of the random variable x is equal to, by definition, arithmetic mean of x is, in terms of expectation, it is e of x. Therefore, by the definition of expectation, e of x is equal to summation x into f of x over all values of x. That is equal to, this is equal to summation x varies from 1 to infinity, x into f of x is p into q raised to x minus 1. Here p is independent of x, therefore this p can be taken outside of the sigma. We get this is equal to, e of x is equal to p into summation x varies from 1 to infinity, x into q raised to x minus 1. On expansion, we get p into 1 into q raised to 0 plus 2 into q raised to 2 minus 1 is 1 plus 3 into q raised to 3 minus 1 is 2 plus 4 into q raised to 3 plus etc. This is equal to p into, here q raised to 0 is 1, 1 into 1 is 1 plus 2q plus 3q square plus 4q raised to 3 plus etc., which is equal to p into, this is the binomial expansion of 1 minus q raised to minus 2. Therefore, this is equal to p into p plus q is equal to 1. Here p plus q is equal to 1 is the condition. Therefore, we can write p equal to 1 minus q. That is 1 minus q is p. Therefore, p into p raised to minus 2. That is equal to p raised to minus 1. That is 1 by p. This is the arithmetic mean of the geometric distribution. That is, arithmetic mean is the inverse of the parameter p. Now we can find the variance of geometric distribution. By definition, variance of x is equal to, in terms of expectation, it is expectation of x minus, sorry, we can use this form. Variance of x is equal to expectation of x square minus expectation of x the whole square. Now, expectation of x is equal to 1 by p. We just derived expectation of x is 1 by p. Therefore, we want to find e of x square only. Now, we can write x square as like this. We want to find e of x square. Therefore, we write x square as x square minus x plus x. We just add x and subtract the same, which is equal to expectation of, here we can consider x square minus x together, and we can take an x outside. Therefore, this is equal to x square minus x is equal to x into x minus 1 plus x. Now, by the linearity property of expectation, we can split this into two expectations. That is expectation of x into x minus 1 plus expectation of x. Here also e of x occurred, that is equal to 1 by p. Therefore, we want to find e of x into x minus 1 only. That is e of x into x minus 1 is equal to, by definition of expectation, it is summation over all values of x into x minus 1 into f of x, which is equal to summation, here x varies from 1 to infinity, summation over x from 1 to infinity, x into x minus 1 into f of x is p into q raised to x minus 1. On expansion, we get this is equal to, we can take this p outside. On expansion, we get for x equal to 1, the term is 0 plus, for x equal to 2, this is 2 into 1 into q raised to 2 minus 1 is 1 plus, for x equal to 3, we get 3 into 2 into q raised to 2 plus etc. The next term is, for x equal to 4, we get 4 into 3 into q raised to 3 plus etc. This is equal to p into 2q. We take 2 into q outside, we get this is equal to p into 2q, 1 plus here 3q square plus here 2 into 3, that is 6 q raised to 3 plus etc. This is equal to p into 2q. This is the binomial expansion of 1 minus q raised to minus 3. Therefore, this is equal to 2 into pq into 1 minus q is from here 1 minus q is equal to p, that is p raised to minus 3, which is equal to 2 into p raised to 1 minus 3 means p raised to minus 2, that is 2q by p square. Expectation of x into x minus 1 is equal to 2q divided by p square. Therefore, we get e of x square is equal to this is equal to 2q divided by p square plus e of x. E of x is 1 by p. And we substitute e of x square in this expression for variance of x. We get variance of x as v of x is equal to e of x square is 2q by p square plus 1 by p, this is e of x square, minus e of x the whole square, that is 1 by p the whole square means 1 by p square, which is equal to 2q plus p minus 1 divided by p square, all divided by p square, that is equal to 2q plus p minus 1 is minus q. Here p minus 1 is equal to from here p minus 1 is equal to minus q. Therefore, this is equal to 2q plus minus q divided by p square, that is 2q minus q is 1q divided by p square. This is the variance of a binomial distribution. Therefore, the standard deviation is the positive root of variance of x. Therefore, standard deviation of geometric distribution is SD is equal to positive square root of variance of x, which is equal to positive root of q by p square, that is equal to root of q divided by p, which is the variance standard deviation of geometric distribution. Now we can find the moment generating function. The moment generating function is denoted as mxt, which is defined as in terms of expectation. It is expectation of e raised to tx, which is equal to summation or all values of x e raised to tx into f of x. This is equal to summation x varies from 1 to infinity e raised to tx into f of x is p into q raised to x minus 1. This is equal to p can be taken outside, p into summation x varies from 1 to infinity e raised to tx into q raised to x minus 1. That is equal to p into summation x varies from 1 to infinity e raised to tx into, here q raised to x minus 1 can be written as q raised to x into q raised to minus 1. Therefore, this q raised to minus 1 is independent of x. That term can be taken outside of this summation. We get p into q raised to minus 1, that is p by q, into summation x varies from 1 to infinity. Here we can combine this as q into e raised to t the whole raised to x. Q raised to x into e raised to tx means q into e raised to t the whole power x, which is equal to p by q into, on expansion we get q into e raised to t. For x equal to 1, the first term is q into e raised to t all raised to 1, that is q into e raised to t, plus next term is q into e raised to t the whole square, plus for x equal to 3 the term is q into e raised to t the whole raised to 3 plus etc., which is equal to p by q into, this q e raised to t can be taken outside. Therefore, this is equal to p by q into e raised to t into 1 plus q e raised to t plus q e raised to t the whole square plus next is q e raised to t the whole cube plus etc., which is equal to p by q into, here q and q can cancelled. The remaining terms are p into e raised to t into, this is the binomial expansion of 1 minus q e raised to t the whole raised to minus 1. This is the that is equal to p e raised to t divided by 1 minus q e raised to t. This is the moment generating function of the geometric distribution. By using this moment generating function, we can find the various moments. Differentiating this mxt and putting t equal to 0 gives e of x. Once again differentiating with respect to t, and if we put t equal to 0, we will get e of x square and so on. Now let me conclude this session. In this session, we just discussed the geometric distribution. We verified that this f of x is a PMF, and we derived mean of this geometric distribution is 1 by p, and we derived the variance of x, standard deviation, and the moment generating function of this geometric distribution. Thank you for listening this session. Have a nice day.